Hello everyone, this is Group 17 present you the multi-pump test rig experiment for this webinar. Before we move on to next part of this experiment, we need to know the objective of the multi-pump test rig. The aim of this experiment is to determine the characteristic and the performance of various types of the pump. So now let us discuss about the introduction part first. Before we start our experiment, it is necessary to know the function of the pumps. What are the pumps when we use the pump? Pumps are devices for supply energy or heat to a flowing liquid in order to overcome heat loss due to the friction. And also it is necessary to raise the fluid to higher level. The heat imparted to a flowing fluid by a pump is known as the total heat. There is a lot of pump being used widely in industry. Each of them own working principle and varies in terms of efficiency and cost. There are 5 types of pump fixed in the multi-pump test rig. The first pump known as P1 is diaphragm pump, second is centrifugal pump, and the P3 is the plunger pump, P4 is the vane or rotary pump, and the P5 is the gear pump. Now it is time to discuss the working principle of centrifugal pump. What are the fluids that can fit into the centrifugal pump? Centrifugal pump can handle dirty liquids or liquids with low viscosity as long as they do not contain air, vapor, or heavy amount of solids. There are one or more impellers contained inside the casing of the centrifugal pump. So the liquid from the source enters the suction pipe and meet the eye of the impeller. So the liquid from the source normally removed the debris or other particles by strainer. As the liquid enters the casing of the centrifugal pump, it rotates in direction of impeller. The impeller works in the aid of the electric motor. As the liquid inside the casing rotates, it creates a centrifugal force and also increases its pressure. At this time, it is now to discharge from the pump, and this is how the liquid discharge from the pump. Oil and energy industry, pharmaceutical industry, chemical industry, food industry, fire protection industry, and last is wastewater treatment plant. These are the list of industries that use centrifugal pump. Why they use the centrifugal pump? What is the importance of the centrifugal pump in their industry? Because the pump are known for the high efficiency with low power consumption, and it is also a very simple design and also known for its durability and low maintenance. This is the reason why this industry use centrifugal pump. Next is the working principle of diaphragm pump. This is how the diaphragm pump works. Diaphragm pump can usually push fluids with high, low, and medium viscosity. There are two bendable diaphragms inside the pump. A diaphragm pump is a type of positive displacement pump that uses both a valve and diaphragm to draw any type of fluid inside the chamber. When the volume of a chamber increases, the pressure in the chamber reduces, and the fluid pours into the chamber. The diaphragm then moves down and forces the fluid out. Once the fluid has cleared the chamber, the diaphragm moves back into position, allowing more liquid to enter. This cycle continues while the pump is operating. This is how the diaphragm pump works. Now we discuss for the industrial application of diaphragm pump. Where does the diaphragm pump used? Diaphragm pump used in oil refinement. Why? Due to their unique design, diaphragm pump can transport large volume of liquid and are ideal for refineries that are located over sizable oil sources. Diaphragm pumps are also far from the wear-resistant that positive displacement pump because there are fewer moving parts or friction points that wear down the component. However, diaphragm pumps do suffer from wings, which is the small gaps in the process that can slow down the flow of the fluid, and the wings and the low pressure are likely to occur over a long distance. We move to working principle of plunger pump part. So how does the plunger work? This is how the plunger works. Okay. Plunger pump convey all liquid medium such as water, oil, or liquid gases over a wide range of temperature. A retracting plunger creates a suction effect in the liquid and open the suction valve. This is called as the suction valve, and the object is moving forward and backward is the plunger. The fluid, the medium flows into the liquid and the plunger then moves forward. The plunger displays the available volume through its own volume and increase the pressure of the liquid to be pumped. The suction valve also close and the pressure valve open the way into the process area for the pressurized fluid. The forward and backward movement of the plunger repeats itself continuously and open or close the valve. Depending on the application, the cycle repeats to several hundred times per minute. Cleaning application is one of the industry that use plunger pump. Why does this industry use plunger pump? Because plunger pump can found reliable high pressure in many industry applications. For example, it is cleaning application or in any process technology in the chemical industry. Displacement pumps are suitable for small or large flow rate and achieve different pressure levels. Even abrasive mediums such as a detergent, slurries or carbon mesh can easily pump via various pressure levels with oscillating plunger pump. Now, this is time to discuss for the working principle of vane or rotary pump. This is how the rotary pump usually works. Vane or rotary pump can handle thin liquids like water and gasoline as well as fluid with low viscosity only. A vane pump is a type of positive displacement pump. It is use the backward and forward motion of the rectangular shaped vanes inside the slot to move the fluid. The slot rotates is eccentrically supported inside a cyclodic cam. The rotor is shielded into the cam by two side of plates. Vane or blades fit into the slot of the impeller. As the rotor rotates and the fluid enters the pump, centrifugal force creates hydro pressure and also push rods push the vanes to the wall of the housing. A tight seal in the vanes, rotor, cam and side plates is important uh, for good suction characteristic described in the vane pumping principle. The industry that use rotary or vane pump the most is the automotive field. A few different parts of the automobile utilize this type of pump, including braking, power steering, automatic transmission, and supercharging. Even some other type of vehicles, including airplanes, use a rotary or vane pump in their system. Inside the pump are a set of wings that are slotted into rotating rotors, which rotates inside the pump housing, or otherwise known as the cylinder or barrel. The rotor is normally offset from the center of the pump housing and cylinder, causing eccentricity. This is the last pump that we going to discuss. This is the gear pump. Gear pump can manage low viscosity liquids like alcohol, solvent or liquid gases, as well as medium and also high viscosity liquids like polymer, melts, gum base or rubber. A gear pump employs a system of meshing of gears, and this is the gear, to move fluid. Because of the mechanism involved, gear pump qualify as a positive displacement pump. For every revolution of gear in a gear pump makes the same amount of fluid moved. Gear pump have two gears that separate on the intake of side of the pump. This creates the partial vacuum, creating suction which draw fluid into the pump. The gear then carry the fluid through the pump and out the other side to the outtake. The fluid are displaced by the rotation of the gear. Due to the direction of and the positive of the gear, the fluid can only flow from the intake side to the outtake side. Gear pumps are mainstay in the petrochemical industry. They are used for crude oil, diesel oil, lube oil, pitch, and bitumen. They are also used for transporting chemicals such as sodium silicate, mixed chemical acids, plastic isocyanates, and other chemicals that must be handled with care. Thank you for watching my part, and I pass to Daniel.
Thank you, Helen, for the introduction explanation. My name is Daniel Syakirin, and now I am going to explain to you about the theory and concept involved in this pump test. Okay, NSPH concept. So net positive suction head is defined to be the difference between the liquid pressure head at the pump inlet and the liquid vapor pressure head at the working temperature of the pump, expressed in the term of length. So we can see that this formula and SPH equals to GC divided by G, and PA minus PV divided by its density minus the HFS minus ZA. We are taking this formula from McCabe book. PA is the absolute pressure of the surface of the reservoir. PV is the vapor pressure of the liquid. HFS is the friction head in the suction. Okay, actually, generally, pump manufacturers design their pumps to work at the maximum efficiency and hence have the relatively lower cost. So, efficiency is related to the pump speed, and so that the speed is fixed to deliver the maximum efficiency that the pump need to have. Okay, so this is the explanation, the definition of the NSPH, the formula, cavitation. Okay, cavitation is a phenomenon where some of the liquid flashes into the vapor inside the pump. Okay, cavitation occurs because of the inlet liquid pressure of the pump is slightly or greatly, only slightly higher than the vapor pressure of the liquid, and this causes eh, some of the liquid to flash into vapor, decreasing the pump capacity and causes erosions. Cavitation is the formation of small vapor bubbles in the liquid then collapse almost quickly as they form. So we have introduced the formula NSPH. It's a measure of how close a liquid is to converting into vapor and cavitating. Okay, NSPH is the absolute pressure that must be present in a liquid for a pump to avoid cavitation while pumping the liquid. Okay, simply defined, cavitation is the formation of bubbles or cavities in liquid developed in areas of relatively low pressure and around an impeller. The imploding or collapsing of this bubble trigger intense shock wave inside the pump, causing significant damage to the impeller inside or in the pump. Okay, one of the causes by cavitation process, if we left untreated this cavitation process, it will cause the failure of pump housing or the destruction of the impeller if we use the impeller. And it will cause also the excessive vibration leading to premature seal and bearing another failure, and it will also consume a lot of power, so we need to prevent cavitation as much as possible. Okay, the next one, we will introduce to you the concept of priming. Priming is where the pump is filled with the fluid that is being transported first before using it to make sure there is no air, gas or vapor that exists in the pump. So in this process, the pump is being filled with the liquid being pumped, and and this liquid forces all the air or gas contained in the passageways of a pump to escape out. Priming may be done manually or automatically. Not all pumps require priming, but mostly do. There are self-priming pumps and also some layout situations where priming is not required. So priming a pump is probably the first and one of the most important thing engineer should do before operating it. Not priming a pump or not doing it properly makes majority of the pump problems. Any problem in pump due to the lack of priming may cause financial impact or high costs due to the pump maintenance and the downtime of the piping system due to a malfunctioning pump. The first formula, when we get H rho Q is equal to C1 rho n power of 3 and d to the power of 5. Looking at the resulting formula, the head and the volumetric flow rate Q is directly proportional to the entry and d to the power of 5. Pump mechanical efficiency according to the Bernoulli equation. This is the Bernoulli equation. The total head H which the pump is required to impart to the fluid liquid is the sum of static head, kinetic head, and pressure head. So since the kinetic or velocity head is negligible for pump, so we will get this formula that appear in the screen, which is H equal to ZD minus ZS. ZD is the static head on discharge side, Zs is the static head on suction side, plus Pd minus Ps divided by rho G. Pd is the pressure on discharge side, and the Ps is the pressure on the suction side. Mechanical pump efficiency, which is Po minus P divided by Pi times 100%. I think that's all from my part. I hope you understand. Now I will pass to Farah to explain about the experimental procedure.
Thanks, Helen. So, I'm Farah Arina, and I will continue by presenting on the experimental procedure of the three experiment for multi-pump test rig. Before conducting any experiment, it is really necessary to do the general startup procedure to avoid any misuse and malfunction of the equipment. First, we need to make sure that the water and oil tank is filled up to at least 50%. Next, switch on the main power supply located on the control panel. The instrument should light up. Next, we should select the appropriate pump and flow rate selector according to the following combination in the table. For the safety, 1. We should never operate the pumps dry. For example, there is no liquid in the pipeline, as it will cause the serious damage to the pump. Second, do not operate the centrifugal pump with outlet valve fully closed for more than a short time. For the positive displacement pump, never do that. As it has no shut-off head like centrifugal pump, if positive displacement operates against closed outlet valve continues to produce flow until the pressure in discharge line is increased, this will cause the line to burst or the pump is severely damaged, or both. Third, always let the running pump to fully stop before switching to other pump. Fourth, always watch out for the direction of the motor impeller. It should follow the direction of the arrow on the pump. Then, let's start with experiment 1, which is the performance characteristic of the centrifugal pump P2. First, press the run button on the control panel to start the motor of pump P2. Second, set the motor speed to about 3000 rpm using the speed control beside the speed indicator. Third one, open the control valve HV8 fully so that the flow rate is at its maximum. Record the flow rate, differential pressure, power, and speed when the readings are stable. Next, adjust the HV8 to increase the flow rate of 70, 60, 50, 40, 30, 20, and 10% respectively. Adjust the speed control if necessary so that the rotational speed remains constant. The next step is we should repeat the step with different motor speed between 3000 and 1000 rpm. Then, from the data that we collect from the experiment, we need to plot the characteristic curve, which is the pump total head, pump power output, pump power input, motor input power, pump efficiency against the volumetric flow rate at different speed. Next, we continue to the experiment 2, which is the performance characteristic of rotary positive displacement pump P4 and P5. First, press the run button on the control panel. Second, set the motor speed to its maximum. which is about 1350 rpm for P4 and 1500 rpm for P5 using the speed control beside the speed indicator. Next, slowly adjust the flow control valve HV15 so that the pump head pressure is at 48% for P4 and 55.5% for P5. When the readings are stable, record the flow rate, pressure, power, and speed. The fifth one, repeat step with different pump head readings for P4 between 45 and 10% and for P5 between 50 and 10% by adjusting the HV50. Adjust the speed control if necessary so that the rotational speed remains constant. The sixth step is repeat step at 1 to 5 at different motor speed for P4 between 1300 and 400 rpm and for P5 between 1400 and 400 rpm. Then, from the data collected using the above procedure, we need to plot the characteristic curve, which is the volumetric flow rate, pump power output, pump power input, motor input power, volumetric efficiency, overall efficiency against the output pressure at different speeds. Next, let's continue on the experiment 3, which is the pulsation characteristic of reciprocating positive displacement pump P1 and P3. First, we need to regulate the motor control until the frequency displayed at the motor panel is less than 30 Hz at the keypad panel. Second, press the run key on the keypad panel to start the pump. Third, slowly adjust the HV8 in the direction of increasing and decreasing flow. Observe the pressure gauge for pulsation characteristic of the pump. Fourth, fix the position of HV8 so that the magnitude of the pulsation is minimum, but beware not to close the valve completely as this will destroy the pump. The next step is we should open the HV17 to activate the dampener. Observe the magnitude of pulsation as it becomes lesser. Now, as I'm done with my part, I will pass to Dan for the next part.
Thank you, Daniel, for the wonderful explanation. So, in this section, I'm going to talk about the result and discussion for our multi-pump test rig. So, the first experiment that we did concerned about pump 2. Alright, pump 2 is essentially a centrifugal pump. It uses centrifugal force to provide enough pump head to the fluid. Okay, looking at this first graph. So the total head decreases as the flow rate increases. We are not entirely sure why this happens. So on top of our head, there's two explanations that we can think of. The first explanation is due to increasing flow rate, the skin friction in the pipeline in the pump increases. So this makes there will be some pressure head loss to heat. So another explanation that we can think of is the pump are unable to provide higher output pressure to maintain that flow rate, meaning to say that it kind of reaches its capacity. It kind of makes sense because you want to maintain a higher flow rate, the pump might unable to provide higher pressure just to maintain that high flow rate. Alright, Another observation that we can make is the total head increases with higher motor speed. So this is obvious because with more motor speed, it means more power. More power means more pressure head will develop in the fluid flow. Let's see these three graphs. So basically it's just difference on the y-axis. It's pump power input, pump power output, and pump power input. So we can say that they are analogous to each other and tells the same story. So when I say this because if motor power input increases, it's obvious that the pump power output and the pump power input will also increase. So I'm just going to simplify the explanation here. So the pump power required increases as the flow rate increases. So this is obvious that we need more power to maintain the high flow rate. And obviously pump power provided will increase with higher motor speed. It's a no-brainer. Alright, so let's look at the pump efficiency versus flow rate. Okay, let's recall what is pump efficiency. It basically tells us how the pump utilizes the power. So basically it's pump output over pump input times 100%. Alright, so the pump efficiency increases with increasing flow rate. We are not entirely sure why this happens, but our best guess was because the flow rate increases, the output pressure decreases. So basically, the pump do not need to work as hard to maintain the to provide the pressure. As at higher flow rate, it only need to output lower pump heads. So another observation we can make is the pump efficiency decreases with increasing motor speed. So it might be due to that with increasing motor speed, there's an increase in frictional force while rotating. So this contributes to heat loss through friction. Friction. So for our second experiment is with pump 4 and pump 5. So pump 4 is the vane pump. Pump 5 is the gear pump. So basically both are rotary positive displacement pump. So basically it traps liquid in a chamber and pushes the liquid into a discharge pump line in a continuous manner. Looking at this first graph, the flow rate decreases with increasing output pressure. So it might be due to, it's the same as the pump 2. It suggests correlation, not causation. So with higher flow rate, it can only output lower pressure as the pump reaches its capacity at high flow rate. So at high flow rate, the pump might not be efficient at providing higher output pressure to higher flow rates of fluid. Okay, let's look at these three graphs. Same as the pump 2 just now, it is analogous. So it is obvious that the pump power required increases. So basically it means it increases as the required output pressure increases. It is obvious we need more power to provide higher pressure to the fluid. But there is something odd that we stumble upon. For the pump power output versus output pressure regarding pump 4. Here, at some point, at some output pressure, the pump power output decreases. We are not entirely sure why this happens. As you can see here, the pump on the right hand side, the pump power input increases as higher output, but the output decreases. So the pump might have contained air as the flow rate is so low at high output pressure, as we can see at the last graph. So in general, pump 4 requires more energy than pump 5. So now let's look at this efficiency graph. So the volumetric efficiency of both pumps decreases with increasing output pressure. So meaning to say that if you want a high output pressure, you might not able to maintain high flow rates. So the pump can only provide that high output pressure to a lower flow rate, fluid flow. It decreases because of the volumetric decreases with increasing output pressure. So it's basically the same explanation that I outlined just now. Okay, let's look at our right hand side. The overall efficiency of pump 4 decreases while pump 5 increases. This is kind of strange that this happens. So let's recall what is overall efficiency. So overall efficiency is basically pump power efficiency multiplied by the volumetric efficiency. So for pump 4, the reason why the overall efficiency decreases, it is because the volumetric efficiency of the pump increases so sharply that the increase in the pump power efficiency do not dominate. So the decrease in the volumetric efficiency dominates, and this gives this downward trend. As for the pump 5, the decrease in the volumetric efficiency is not enough to dominate the increasing pump power power efficiency. So overall it increases. So a conclusion that we can make here is that pump 5 is better suited to work at high output pressures, while pump 4 is better to be used in lower output pressure. Okay, for our third and last experiment is regarding the pump 1 and pump 3. Alright, so for the pump 1 is the diaphragm pump. Pump 3 is piston pump. So we did that. So both pumps are what we call reciprocating positive displacement pump. So they work by trapping the liquid in a chamber and pushes it in a discharge line. So it is the same as the rotary positive displacement pump that we discussed just now, but reciprocating positive displacement pump work in a discontinuous manner. So basically it sends a pulsation of fluid flow And this pulsation means that the pressure reading in the pressure gauge fluctuates. So it is hard to get a reading on the on the pump. A more advanced treatment might need to analyze this pump. So there's a way that we can do that by introducing a dampener. Alright, so we did some observations with a dampener or dampener. A dampener basically reduces the pulsation that this pump creates so that it becomes more stable. So without the dampener, the fluctuations of the needle is intense. And the vibrations are also very loud to the point that we were actually worried and we actually called the technicians if this is normal, and he said it's completely normal, so all is good. So with a dampener, the fluctuation in the pressure gauge is reduced significantly, and the vibrations are noticed to be significantly quieter. So in the future, we can do some analysis by using the dampener, but the dampener might reduce the pump pressure, so we have to take that into the account if we want to do a quantitative analysis. Okay, so that's all from me with the result and discussion. So I'm gonna pass to Daniel for the improvement that we can make in the future. There you go, Daniel.
Thank you, James, for the explanation about the discussion and results. So now I will talk about the improvement that needs to be made for the future experiment. Okay, first one. During the experiment, the speed of the motor is extremely hard to set. The speed reading fluctuates very well with the area of plus minus 2000 rpm. So, our suggestion is the test rig should install some sort of stabilizer to stabilize the rotation of the motor. In this way, we can get a more accurate data from the test. When taking the pressure readings, do not just rely on the computerized readings, or we just take the data literally. So it is advisable to cross-check the pressure computerized readings with the pressure gauge installed between the pumps. So we need to calculate, and also we need to see and observe with our eyes at the pump. Other than that, the pump could not operate at more than 30 Hz, and the pump could not work when it is below 20 Hz, especially for pump 3 and pump 4. During the experiment, large variation on motor speed cannot be obtained, and the trend in the different speed could not be obtained. So it is better to replace the pumps that could handle large variation of speed and do a maintenance check of the motor of the pump regularly. Next one, it is also advisable to take more readings between the ranges to make the characteristic of the curve smooth and more reliable. It is the best to place the pump closer to the water source so that we can achieve a better priming time. For our group, we are from group 17, and thank you for your focus during our long discussion in this experiment. Thank you.